Thank you very much for arranging all these visits and the seminars, Andre. And I'm very impressed how many students or postdocs, researchers here. It's a big institute. I'm very impressed by this, your institute. So today, my talk is not organized compared to Oleg's talk. I may talk about something something I haven't understood, like the supercurrent-induced spin Hall effect, and I want to maybe give some motivation and try to discuss what we have understood and what we have not understood. The first part is maybe more clear. I'd like to discuss spin and charge conversion mechanism called spin Hall effect and inverse Hall effect, and discuss some theoretical aspects. So this is the work I'm continuing with Hiroshi Kono in Nagoya and Aurélien Manchon in Marseille in France. Okay, so just before, I start with introduction general, which may be obvious for you too, but spintronics. We are doing spintronics and we are trying to manipulate conduction electron spin as well as charge. So far the electronics deal with just electron charge. So electron is just some particle with charge. But in fact, they have a spin. And the spintronics want to make use of each spins the electrons are carrying. And so the subject of the page is hidden, but this is not intentional. But anyway, so this is the idea of how spintronics can be useful. And the original idea, so manipulated electron spin means that we can have a electric power, electric current, which is spin polarized. Like if we have this type, we can have only up spin electron, and this type gives only down spin. So spintronics aims at creating such type instead of just spin mixed electricity. So what we can do with this type is very easy, obvious, because by injecting electric spin current from this type, we can manipulate or flip the magnetization. So that can be used to store information. And so if we make lots of this small this structure, we can have a random access, magnetic random access memory where we keep all the information in small magnet and and write and read the information by use of this spin current. And in fact, so this is a story which we have been saying and never, realized until recently, but just a few years ago, I heard that this kind of membrane is already in many rather not expensive smartwatch from Huawei, carries this kind of new membrane device. So that I didn't know, and I don't know why companies make it secret, but hearing this, I think that I have to buy this smartwatch. And why they are using this is obvious, because MRAM consumes low energy, because we don't need, these are non-volatile, so we can cut the electricity totally, but keep all the memories. And so what they say is that those smartwatch the battery lasted just few days before MRAM, but when they carry a MRAM, the battery life became longer than 1 week. So these are quite really useful and becoming more familiar to us. Okay, so this is one of the applications of the spintronics. But here, I'd like to discuss a little bit more, maybe not useful for industry, but fundamental effects in spintronics. That is called the spin Hall effect. So that is a spin Hall effect is the effect where we apply electric field to create a spin current. And for this we need a spin orbit interaction. Very simple physics, because spin orbit interaction couples the momentum of the electron and the spin. So in general, we expect that if we drive electron with a spin in one direction by electric field, then the spin orbit selects the spin. So like up spin goes to this way and the down spin goes the opposite way. So what it means that we have a spin current created in the perpendicular direction. So by use of spin orbit interaction, we can easily create a spin current from the electric field or current. So this is called the spin Hall effect. And so as the conventional explanation for this effect is like this. So first we apply electric field and create a spin current because of this. So we have a spin Hall conductivity that connects the spin current and the electric field. And if we have a spin current, then at the edge, the spin accumulates. So at the end, what we have is a spin profile like this, where up spin accumulates to the left edge and the down spin accumulates at the other edge. So that's the explanation of how spin accumulation is created by the electric field, by spin Hall effect. But here, there is a fundamental serious problem in the theory, because the spin current is not uniquely defined, because it's not conserved current. We can modify the definition as we like in principle. So the spin Hall conductivity is not well defined. And that arises from the non-conservation. So that unlike charge, in the case of charge, everything is very uniquely defined. So the conductivity is unique, but not for the spin Hall effect. And so to avoid this fundamental issue, I'd like to describe the effect by use of direct response of spin density and electric field. The spin is well defined. It's physical quantity, no ambiguity, and electric field is also physical. So by constructing the direct relation between S and E, we should have very clear description. That's what I wanted to do. But this idea was already argued in almost the first proposal of the spin Hall effect, where they try to discuss spin density created by the electric field. But the theory was not so, just brief theory. And also after that, people started to discuss spin current because it's more fashionable and more money comes to the spin current business. Anyway, so what I'd like to do is a spin Hall effect in the linear response theory. So I want to calculate the spin density as a function of the applied electric field. So the coefficient here is what I have to calculate. And this is just a spin and electric current correlation function in the sense of linear response. So it's straightforward to calculate, but we see immediately that the uniform component vanishes. That means if we apply electric field, there is no uniform spin polarization. But this is obvious because we know that electric current doesn't produce magnetism. And this is because if the system is symmetric, this should be 0, because spin density and the electric field, they have different symmetry with respect to inversion and time reversal. So the coefficient must be 0. But considering the spatially varying component, we have finite coefficient. In fact, if we expand this coefficient in correlation function in terms of the external momentum, Q, then we see that there is a linear term proportional to the spin orbit interaction of the system. So that means that, and of course, and there is some additional anti-symmetric factor, meaning that the spin density is created by the gradient of electric field, but in the rotation of the electric field or rotation of the current. So what we obtain in this way is, I calculated this coefficient in a Green's function method, and so this is a result. So the spin density indeed is created by applied field or the current, but proportional to the vorticity. So if the current has vorticity, this rotation becomes finite, and then we have a spin. What it means is that, okay, so if we apply electric current in any material, in any sample, at the edge, the current must be 0. So that means even in the center area, the current may be almost homogeneous, but at the edge, there's a difference. So the rotation of the current appears at the edge when the current disappears. So at the left edge, we have a vorticity in the up direction, for instance, and then the right edge, we have a down because the electric current is decreasing in this direction, increasing in this direction. So they have opposite vorticity, and this my result indicates that the spin density is induced proportional to the vorticity. So we have up spin accumulation here, down spin accumulation here. And this theory is, of course, there's no ambiguity because everything is physical quantities. So for me, so this formula is the essence of the spin Hall effect. But perhaps not, this idea is not supported in the community. Okay, and so this is rather beautiful because just rotation and coupling of the spin and current. But in reality, we have to include some diffusive motion of the electron because all the metallic system has a disorder and the electron behaves diffusively. But this is also done in the same scheme by use of Green's function. Just include the vertex correction, which represents the diffusive motion. And then we have a response function with diffusive factor. And eventually the spin density becomes a little bit complicated, but roughly speaking, this is just a diffusion. So at the edge, there's a rotation of the current or the applied field, but this effect is extended to with a finite decay length. And this corresponds to the spin diffusion length. So what we obtain is the spin density accumulates near the edge within the distance of spin diffusion length. So then this final result agrees totally with the conventional picture of the spin Hall effect. Okay, so this is one spin Hall effect. And now I'd like to consider the inverse effect too. So this is a spin Hall effect we have discussed, but there's an inverse effect. Means when we inject a spin current, the spin orbit interaction converts the current into the charge one in the perpendicular direction. It's like looking at this diagram in the opposite way. So on the general, of course, this like here we see that these effects looks like reciprocal. But I'd like to discuss that maybe they are not reciprocal at all. It looks reciprocal, but mathematically. So what I do is the same correlation function, linear response theory. So the spin Hall effect, we calculated the spin density as a function of the applied electric field that is represented by the vector potential. So the coefficient we have to calculate was spin and electric current correlation. And the inverse effect is like this, that we calculate as electric current induced by some magnetic field that drives the spin current. So again, here the correlation function is current and spin. So we see that the response function satisfy, they are almost identical, just an exchange of the index. So, and we have calculated the spin Hall response and found that there's a linear spatial derivative term. And we can, of course, do further expansion in terms of the external frequency or dynamics. And then we can just write down the expression of the spin density to find that there is a spin density is induced by the applied field, magnetic field, and the time derivative of the magnetic field. And the coefficients are here. And the Maxwell equation means it tells us that B dot is rotation V. And this is exactly the spin Hall effect we have explored. Okay, and of course, the first term is more obvious. The magnetic field creates a spin density. And looking at the inverse effect, the same coefficient describe the current like this. So the first term proportional to this C0 constant represents, in fact, the spin Hall effect, because usually what they believe is that applying a spin current, so this is essentially spin current. Spin current is converted to the charge current by spin-orbit interaction. And the second term is dynamic, so we need some dynamic spin current, but that's not what experimentalists are usually doing. So as far as I understand, the experimentals believe that inverse spin Hall effect is like this expression, and spin Hall is this. But we see that the coefficients are not identical because this spin Hall coefficient is a linear term of the external frequency that correspond to the higher order dynamic term. So that means that the spin Hall and the inverse spin Hall effects amplitudes are generally totally different. And so my conclusion in this small easy calculation is that spin Hall and inverse spin Hall effects people believe are not reciprocal. And I started to ask experimentalists, but so far the experimental results are not quantitative enough to see the difference. So they still believe they are reciprocal, but I'm trying to study more and to see if this is the case or not. And here we see that what they believe is inverse spin Hall is just Ampere's law of the Maxwell's equation. So we may have a more different explanation for the effect. So this is the conclusion of a clear part of my talk. And are there some questions so far, or maybe later? And so I started this because I wanted to study the spintronics by use of supercurrent in superconductivity. So, sorry, the supercurrent spintronics, the title is supercurrent spintronics. Already there are many experiments trying to use supercurrent in the SNS superconductor normal super junction to create a spin Hall or spintronics effects. Like this is an experiment by Stuart Parkin group in Germany, where they use a niobium superconductor attached to this manganese germanium, or this kind of antiferromagnetic structure. And then they injected supercurrent by use of niobium lead to this magnetic material. And they argue that the super spin current has been created in this way. And so I'd like to theoretically see if spin Hall or those spintronics effect can be really induced by supercurrent or not. Because supercurrent is dissipationless. And that is rather, it's not obvious if such supercurrent can induce spintronics effects, because many spintronics effects causes dissipation. So magnetization flip or spin charge spin charge conversion or those, there are many dissipation sources. So I want to understand to what extent the equilibrium supercurrent can induce spintronic effect. That was the motivation. And okay, so maybe I just briefly explain what are the supercurrent. So if we have two superconductors and attach them together, in general, there is a supercurrent proportional to the phase difference of the superconductor. And this is dissipationless because there is no voltage. And we can consider the supernormal superjunction, where this is normal metal with dissipation. But if the distance, the normal junction is, normal layer is not thick, we have a overlap of the superconducting overlap parameter, and that then supercurrent still can flow in the normal region. This is a supercurrent, and I want to calculate spin Hall effect induced by this supercurrent. And yeah. So that's, but theory, so from here is not the finished part. So I just briefly explain the idea. So what we, sorry, the title I forgot, but this is how we formulate a supercurrent in SNS junction. In the superconductor side, we have a pair creation because superconducting order parameter is a pair, so that two electron up and down spin can be created or annihilated. So in the diagram like this, we can calculate, we can represent a supercurrent like here or here. Means that the current operator is here, but the superconductors creates the opposite direction of the electron propagation because the superconductivity creates pair or annihilates. Compared to the normal current, this is obviously different because normal current case, the electron propagates always in one direction, while including a superconductivity, we have a kind of opposite propagation. And this is called anomalous Green's function, and this is a feature of the supercurrent. By knowing this, it's almost obvious how to calculate the spin Hall effect created by supercurrent. And the diagram actually looks very similar. This is a normal current spin Hall effect in the normal metal. The electric field induces the current and the spin is created by the spin-orbit interaction. In the case of superconductivity, we have this superconductors creating a supercurrent, but the diagram are essentially the same, and mathematically we can show that this anomalous propagation gives essentially identical answer to the normal state because the response of electron pair propagation and the particle Hall propagation, they have mathematically the same amplitude. So from this we can see that supercurrent can also induce a spin Hall effect just as the normal, like the normal current case. And here is one expression, a little bit complicated, but essentially the spin density created by the spin Hall effect is proportional to the Josephson current or the sign of the phase difference. So we can do spin Hall effect by use of the superconductivity too. And maybe this is fine and maybe obvious, but now I'd like to consider inverse effect. Inverse effect means we create a spin current and then the spin of it convert this spin current into the charge current in the perpendicular direction. And then this may cause a problem because this is the this additional current is the same direction as the Josephson current, and so either this current is dissipative or non-dissipative. We have to see if this is non-dissipative or not. And also, it may change the whole equilibrium supercurrent. So anyway, so that's why, okay, the question is, sorry, I didn't put any result, but diagrammatically this is easy or straightforward. We can just include the spin orbit interaction and the spin current source to calculate the charge current. We can easily show that there's a current along the Josephson direction. But, and this is the same as normal case. But this current, for me, it's still, I don't know if this current is dissipative or supercurrent. So far, I haven't found how to judge the current induced by the inverse spin Hall effect is super or non-super. I mean, there's no way so far to see the difference theoretically. And so still I'm trying to figure out. But at least one thing sure is that if we have a spin current, inverse spin Hall current, this current modulates the phase because the original Josephson relation is modified. So what I expect or what will be the answer will be like this. Without the inverse spin Hall effect, the Josephson relation is here. So the current is locked to the phase difference of the superconductor. And there is an equation motion for this phase and the current. And so this Josephson effect is realized at the steady state. Including the inverse spin current, we have additional current. And if this is static, what I expect is that eventually the system goes back to the steady state by modulating the phase. If the phase is modulated, this additional current is absorbed. So I expect that at the end, this spin current creating the inverse spin Hall current will just modulate the phase. So in that sense, we can use the spin accumulation or the spin current to modulate the phase of the superconductor. But I don't know how useful it is. Yeah, so this is a diagrammatic explanation of what I said. So if we inject a spin current or in this normal region, we'll create an inverse spin current modulating the phase. That's what we expect, but the theoretical calculation has not been finished. So this is partially expectation. Okay, that's all. And so still, calculation is going under. So this is a summary. I talked about something not related, but the first part was the spin Hall effect and inverse. So this is not Ampere's law, sorry. But anyway, inverse and direct spin Hall effects, the coefficient seems not reciprocal, and this must be cleared by experiments. And the second part, I wanted to formulate a supercurrent spintronics by diagrammatic theory, but there's some difficulty I have to overcome. But maybe the question here is that supercurrent is dissipationless, but then that should be not useful because dissipationless means they cannot do work to outside. So it should be useless, but I want to understand theoretically what the supercurrent spintronics can do. Like steady spin accumulation may be okay, but they are equilibrium, so they cannot do work and useless. Then anyway, I want to understand the phase dynamics and the spin transport dynamics and solve everything together. That's what I'm trying to do now. So this is the end, and so I'd like to just introduce about RIKEN. RIKEN is an institute in Saitama, Wako City in Saitama, which is like 50 kilometers from Tokyo. And we have lots of programs for international researchers, like we can accept the students, PhD students and with salary for period of 3 months up to 3 years, and RIKEN can help the doctor's degree. And of course, we have not a small number of postdoc position, researcher positions, especially the special SPDR. This is a special position with a rather high salary in Japan, as in Japan. And so if you are interested in doing postdoc, please apply. And also for big professors, we can set up an invited professor position too. So if you are interested in coming to Tokyo area, which may be boring compared to this place. But anyway, please contact me. So thank you very much. And